also a little bit of a discussion of it, not tonight, but next Monday night in lab. So this is another way of thinking about the respiratory duct and the alveolar duct and the alveolar sacs. We talked about last lab, right? You have your alveoluses, overall alveoli. This whole thing will be an alveolar sac, and we can see the pulmonary capillaries, and we can barely see some little lines, which represents the elastic tissue that wraps around them. Let's learn how these things work. Your favorite topic, vocabulary. All right, pulmonary ventilation is defined as what? Air in and out of the lungs. That's simple. Right, when someone's being ventilated, they're simply just moving air in and out of their lungs. That part's easy. Let's practice our learning from pictures skills. Nobody say anything out loud as. Think about how you would describe that. Because that's the definition of external respiration. Take a look at it. What is it trying to tell you in picture form? Don't say it out loud. So what is it trying to tell you in picture? And then look at the one on the right side, anatomical left, and see how it's different from the one on the anatomical right. If I can teach you guys how to look at a picture and learn from a picture, learning's a lot faster. There's a lot less reading to do. All right, so when I look at the one described as external respiration, I notice that there's an alveolus. I notice a pulmonary capillary. I see oxygen going from the alveolus into the pulmonary capillary, and I see CO2 going from the pulmonary capillary into the alveolus. And so I realize, oh, they're exchanging gases. They're exchanging gases between the lungs and pulmonary capillary. That is what external respiration is. The exchange of gases between the lungs and the pulmonary capillaries. Given that same way of thinking, then don't say this out loud, but how would you then describe what happens with internal respiration? Think about how we describe the external, but now apply that same format to the internal image. And what you should come up with is, well, with like the exchange of gases between systemic capillaries and tissues of the body. Which is what it is, because we're just, O2, CO2 being exchanged from the systemic capillaries to the tissues. Now let's test somebody's memory. But again, keep the answer to yourself for a moment. Give everybody else a chance to shake their cobwebs. What other type of respiration is not up here? Look at the pattern. Look at what they've done. What are they not showing you that you hopefully learned about in 211? You're like, what the hell? I didn't learn anything else in 211. So look at the way they're doing this. From lungs to capillaries, then bring it to the tissues. From capillaries to tissues. And what are tissues comprised of? Cells. Is there any other place where you can exchange gases? Maybe inside the cell? But I can't hear you. Cellular respiration, right? Exchange of gases between the mitochondrial membrane. So we'll get to that one later. Now, all of this depends upon your trivial pursuit default answer from almost any question in physiology of why something happens. It's a pressure gradient. I mean, if I were to ask you why is oxygen going from the alveolus into the pulmonary capillaries, by now you should catch on and go, oh, well, it must be going from areas of high to areas of low. And why is CO2 from the pulmonary capillaries going into the lungs? Because of the boring answer. It's going from regions of higher to regions of lower. That's why anything happens. And we're going to be working on these. So right now, just ignore the numbers. We'll get to those buggers a bit later. All right, now, to understand how we ventilate, we have to look at Boyle's law. And this is a variation of, if you guys remember from chemistry, P1, B1 equals P2, B2. Yeah, something like R2, D2. We're going to learn them as P is equal to 1 over V. All right, pressure is equal to the inverse of volume. Learn it this way, and then realize in this form, we're going to be manipulating the volume to cause changes in pressure. We're going to be manipulating the volume to cause changes in pressure. Later, we'll screw around with it and change the pressure to change the volume. But right now, we're going to be looking at changing volume to cause a change in pressure. And that's dealing with Boyle's law. All right, so here's an example of how Boyle's law is going to work. You guys are exposed to the anatomy of the respiratory section, the chest, the lungs, and the pleurocies, right? The parietal and visceral pleura. And this is my attempt to try to use PowerPoint to make a picture. So I made the big black line your parietal pleura. Remember in lab I said it's actually connected to the diaphragm. And this little inner box is both the visceral pleura, but also the outer lining of the lungs. And therefore this space is the lung volume. And this will be basically your conducting system, right, coming into the lungs. Now when the diaphragm is contracted, right, it becomes more of a flattened shape, more of a dome shape when it's relaxed. When I contract it, it becomes more of a flat. And since it's connected to the parietal pleura, if I contract the diaphragm, I pull on the parietal pleura, and what happened to the space between the visceral and parietal layers? It got bigger. According to Boyle's law, what happens to the pressure in that intrapleural space? Mary, do you know? The volume is bigger, what happens to pressure?
Down.
Right, pressure goes down, right? Because inverse relationship. So the pressure dropped. That will allow the lungs to expand into that larger area, which I couldn't make PowerPoint do very easily, right? So the lungs will expand into here. And when the lungs expand, right, the volume is a little bit bigger here than it is here. And if the lung volume gets larger, what happens to the pressure in the lungs? It also goes down. Then all we got to do is go the other direction. What if I have my diaphragm relax? Then it pushes up on the parietal pleura, making that intrapleural space get smaller. Well, if volume goes down, what happens to pressure? It goes up. That pushes against the lung tissue, making the lung volume go from this space to this space. We made the lung volume get smaller. Again, if lung volume gets smaller, pressure goes up. And all we got to do is contract and relax the diaphragm to cause these changes in volumes, which lead to changes in pressure. Let's see how we do this. Now, one thing that's going to happen a bit later is, let's pick on Mary since I already picked on her once, right? She gets upset because I picked on her, so she stabbed me in the chest with a lightning bolt. So there, she's just stabbed me, right? There's a big hole in my chest. Now there's a gaping hole to the outside world. When I contract my diaphragm and pull it down, yeah, making this volume larger, what happens to the pressure in that space? Why does nothing happen?
Because air comes in from the outside.
Because now I'm getting air to come in from the outside, right? Does anybody know what that? I know at least one person knows what this is called. Stefan, what's this called?
Pneumothorax.
Pneumothorax, or maybe what's another name for it? Perhaps sucking chest wound, kind of an issue, right? And we really need to plug that hole up because right now, Boyle's law won't work because, as Dave said, we're pulling air into this, and that's not going to allow us to actually change the volume. It actually causes the lungs to collapse a little bit, and we're going to see how that works by the end of 2 lectures. All right, let's walk you through how we can use Boyle's law to do pulmonary ventilation. Look at the pressure in the atmosphere outside, right? And right now we're going to pretend it's 760 millimeters of mercury. That's the pressure in the outside. Tonight, when you guys are at home with a friend or a partner, I want you to put your hand under their nostrils and let them breathe normally. And tell me what you notice. You'll feel air blowing on your fingers, then you feel nothing, and then you feel air kind of blowing past your fingers back up into their nose. So what I want you to notice is the period of someone's breath when there's no air moving. Why would there be no air moving in and out of the lungs? Well, why does blood not go from one place to another? Why do ions not cross the cell membrane? Because of equilibriums. The pressure must be the same in the lungs as it is outside if there is no air moving down my conducting system. And that's what happens at the end of each phase of breath. You guys inhale for 2 seconds, and you exhale for 3 seconds. So watch somebody breathe later tonight or tomorrow, right? Put your hand under the nose and feel the breath of air going out, pause, the breath of air coming in, and the pause. At each pause, we have the pressure the same in the lungs as it is in the outside atmosphere. So let's get us to inhale. We're going to take our diaphragm, right, and we're going to contract it. Bingo, contract the diaphragm. And then I know from this, right, well, not from that part, from this part, when the diaphragm contracts, I make the intrapleural space larger, which makes the pressure lower. And if the pressure lowers in there, I can get the pressure in my lungs to lower, which allows the lungs to expand, hence these black arrows. Well, let's compare the pressure in the lungs to the pressure in the atmosphere now. The atmospheric pressure won't change as long as there's no storm moving through. But look what happened to the pressure in the lungs. It used to be 760. Now look what it is. It's 758. Not a very big change, but it's enough to create a gradient. It's enough to have air flow into your lungs. Doesn't have to be much.
This is air going in or air going out? Inhale or
Follow the arrows.
So in. So you're inhaling.
Yeah.
Okay.
Yeah. Air is moving into your lungs, and as long as you continue to contract the diaphragm, you will continue to expand the intrapleural space. You will continue to expand the lungs, and as air rushes in, you keep expanding the lungs. You keep dropping the pressure as more air moves in until you finally stop expanding the lungs. Then the airflow catches up, and you're back to equilibrium again. Whether it's a short breath or a prolonged deep inhalation, whenever you stop, that's because the pressure will then be the same inside and outside. Now, I want to push the air out of my lungs. Well, if contracting the diaphragm allowed me to lower the pressure in the lungs, which caused them to expand, then what if I relax the diaphragm? It'll then push up against the parietal pleura, making the lung volume get smaller. And when lung volume gets smaller, the pressure goes up, pressure goes up. Look how much it went up to. Not a whole lot, 763. But outside 760, there's still a region of high in the lungs compared to the outside atmosphere. And you're simply pushing the air now out because it's following a pressure gradient. And it's that simple. Air moves in because the lungs are a region of lower pressure. Air moves out because the lungs are a region of higher pressure compared to the atmosphere. And all we got to do is contract and relax the diaphragm to make all these changes take place. And notice that when we inhale and exhale, we're not changing the pressure a lot. We're not going from like 760 to 300. Right? It's 3 or 4 millimeters of mercury. That's enough, though, to get air to flow in and out. Well, let's talk about this breathing pattern we just did with boils. Right now, all of you are hopefully nice and relaxed, even those of you that haven't had a lab practicum yet, right? And so you're doing normal respiration called eupnea, right? Nice, normal, relaxed breathing. I know the muscles that are involved in inhaling under relaxed conditions are going to be the diaphragm and your external intercostals. Those two muscle groups are involved in relaxed inhalation or inspiration. It's the same way of discussing them. Diaphragm and external intercostals. Contract both and air will flow into your lungs. Now let's do relaxed exhalation. Let's expire, push the air out of our lungs. You gotta think about one of the characteristics of muscle tissue, right? It's elasticity and its desire to recoil back to its original smaller size. So you don't need any impulses to make the muscle relax. You actually stop sending signals. So those of you that had me for 241, remember one of the things that determines the duration of a contraction was the duration of what? The neural stimulus. You stop sending signals to the diaphragm and says, oh, I get to relax. And I go back to my little dome bowl-shaped orientation. That pushes against the lungs. The same thing for the external intercostals. They relax and your chest falls back down onto itself. So relaxing muscles is passive. You don't need to contract any muscles. Plus, you know some anatomy about the alveoluses. Isn't there some kind of tissue that wraps around every single one of those things? Right? And elastic fibers are like rubber bands, right? When you inhale, you stretch them out. They don't want to be stretched. They want to recoil back to their smaller size. That's assisting you in exhaling. It's actually a force you have to overcome when you inhale, because you got to stretch all those fibers out. That's hard work. But they want to recoil back, so that's a nice little passive exercise. So to exhale under normal resting conditions, no muscles work. It's simply recoil the elastic connective tissue and recoil the muscle tissue. Saves lots of ATP. Remember, the key is that's under relaxed conditions. Now, relaxed inspiration is resisted, and this is why we had that conversation on Monday about those pneumocyte type 2 cells, otherwise known as septal cells, creating that surfactant that went into the layer of water that lines the inside of every single alveolus. That creates surface tension. Those water molecules that line the inside are making hydrogen bonds like shaking hands, and they want to stay hooked up to each other. But if you take your alveolus, which I can make one really large one here, and give it a layer of red water, I'm going to exaggerate the layer of water. Ooh, blood red, there we go. All right. Ooh, that smells nice. H2O, H2O, right, H2O. I have to break those hydrogen bonds. Whenever I want to expand the alveolus, make it bigger like this, then I have to pull apart the water molecules. I have to break all those hydrogen bonds. Uh-oh, there it is. And that takes force to break all those hydrogen bonds. So those septal cells that created that surfactant, right, helps to reduce the number of hydrogen bonds. It makes it easier for you to expand your lungs with the addition of surfactant. To have you appreciate surface tension, two things. One, look at that little dude. All right, it's a water strider. And you can actually see him striding the water. If you look carefully, we can dim the light so we can all see this more clearly. That dude, there we go. I can see the depression in the water, those divots. And what that bug is actually doing on a side view is, if this is the surface of water, it dips down kind of like this, and then here's my bug and his little feetsies. He's actually pushing down. His mass is pulling down and stretching and stressing those hydrogen bonds made by water. If I could add maybe a grain of rice or two to their back and make them weigh enough to actually break the surface tension, then they would sink. But this is what's happening in your lungs. You're trying to stretch out those water molecules. That takes a force to do. Try this at home to really appreciate the science. And you can tell your little kids that it's actually magic instead. I remember all my colors. Take a glass of water, fill it to the rim with water, and then take if you have an eyedropper or a pipette or maybe just a teaspoon, start adding more and more water until you notice that the actual edge of water is literally past the edge of the glass. Like an invisible force is holding up that little teeny miniature wall of water. That's surface tension. That's hydrogen bonding. And when you add that one extra little drop of water, it'll add just enough mass, enough weight for the force of gravity to pull apart those hydrogen bonds, and the water trickles down the side of your glass. But that's a nice little tangible experience of the actual strength of hydrogen bonding. That's a fair amount of water you're holding up with that. Or you can simply do what this guy does. Do you know what that is? It's a basilisk lizard. That's really boring. Basilisk. But you're close. No. Its nickname is the Jesus Christ lizard. Yeah. Because it runs across, apparently, the surface of water. It's actually not really doing that. It actually does sink a little bit. But they're fun to watch. All right? We just did relaxed breathing. Let's talk about forced breathing and the muscles that are involved in forced breathing. So apparently, the muscles involved in inspiration are exter, scalene, pecmen, sternocleidomastoid. What in the hell are those? Do you guys remember? Yeah. Diaphragm, external costal, scalene, pectoralis minor, and sternocleidomastoids. Right? Why did I write it this way? Intentionally, as an example of how you guys should be taking notes. Shorthand. If you know the conversation, abbreviate. If you need to, later the next night, go back and go and elongate the names when you have more luxury, more time. And I'm going to be probably stressing this more and more because I just got an email from a student who is in PT school. And I had her for Bio 160, 241, and 242. And she's stressed as all hell because the faculty will not allow them to record lectures. So you got to be fast at taking notes. How are you fast? You learn to abbreviate, right? Because look at the ones below it, right? So this was forced inhalation, right? What muscles do I use for forced expiration? Oh, ra'io-ata. Sounds like I'm speaking Egyptian almost. Right? What do those things stand for? Well, I know they're abdominal muscles, so that would have to be the rectus abdominis, external oblique, internal oblique, and transverse abdominis. Don't write the names out, for God's sakes. Abbreviate. Never write the word anterior from now on. It's ant. Pos for posterior. Right? Create your own little symbols or stenography to help you take notes more efficiently, but also more quickly, so you're less stressed during classes. Now, think about the scalings. I know that my 241s had to learn scalings. Those of you that didn't have it for 241, did you guys have to learn scalings? Right? Well, here's the cool thing. They go, where do they go? They're going to go from the transverse processes of the cervical vertebrae to your first couple of ribs. And they're going to lift your ribs up. If I lift my rib cage up, I expand my lung volume. And if I expand the lung volume, what happens to the pressure in the lungs? It goes down. So you can inhale, right? And the same thing with the sternocleidomastoid, right? It goes from here, the sternum and the clavicle, up to the mastoid. So if I yank on it, I'm going to be lifting my rib cage up. And that's what I will use if I want to quickly, forcibly inhale. So the next time you guys have to run to your car and you're huffing and puffing when you get there, those are the muscles you're contracting. So I can force more air in more quickly. Now the abdominal ones, think about how they're working, because we're not really compressing the rib cage when we're working with these abdominal muscles. Because where do your abdominal muscles run? In the abdomen, right? Remember, rectus abdominis runs this way, but then the external, internals, and transversals are all off to the side. So to really see how these guys work, suck your gut in. Come on, suck it in, and now try to take a deep breath. It's hard to do, right? And really, if you suck your gut in, walk around all day like this, and see what it's like to be 9 months pregnant, apparently. Right? Because that's what's happening when you're pregnant. That big, gigantic 8-pound parasite, right, is sitting on your bladder, pushing your stomach backwards and up along with your lungs. That's why it's hard for women in their last trimester to take a full breath of air or to eat a whole lot in any one sitting and pee every 10 seconds, right? Because Junior's doing the trampling on your bladder. But that's how the abdominal muscles work. When I contract my abs, I push my guts in and up, and that pushes against my lungs, pushing the air out. That's why you breathe really deeply from the diaphragm, right, to get the muscles to work. All right, compliance, that's really about how easy it is to breathe. Think about what the word compliant means, right? Do you cooperate? Well, if you're high in compliance, it's easier to breathe in and out. And if you're low on compliance, it's harder for you to physically move air in and out of your lungs. This is more about ventilation than it is gas exchange. What are some things that can make you more or less compliant? Well, think about connective tissue around your alveoluses. What if your elastic connective tissue became scar tissue, where it wasn't stretchy? And now you try and expand your lungs against non-stretchy material. It's not going to be easy to do. If you have lots of fluid inside your alveoluses because you've got pneumonia, more fluid means more hydrogen bonds. It's going to be harder to expand, and even the thickness of mucus that might accumulate in your lungs. Mucus is very viscous, much more so than water. It's even harder to pull apart those molecules. And that can make your compliance go down low as well. Or try this. Have a friend wrap an ace bandage around your chest after you've exhaled. Or put a belt around your chest and then tighten up and try and breathe in. That restriction makes it harder for you to breathe in. So it's sort of like what scar tissue can be like. You have to now try and stretch out that tissue. Let's look at how much volume of air we do move through our lungs. And the one I truly, truly want you to memorize is the tidal volume one first. Right? That's 500 milliliters. Think about when you go to the beach. You watch the water rush up on the shore and then it pulls away from the shore. Right? That's why it's called tidal volume. It's the flow of air in and out of your lungs. Let's watch how this works. When the red line goes up, that's inhalation. When the red line goes down, that's exhalation. So we breathe in 500 mils, we exhale 500 mils. We breathe in 500, exhale 500, and that's you, just your normal everyday breathing. Now, the next category is inspiratory reserve. Break that apart for a moment. Inspiratory, to inspire, to inhale. What does reserve refer to? This is the quiet room. I'm going to just stare at all you guys. Right? You guys know what reserve refers to?
It's like the total capacity, you know?
It's which?
The total capacity.
No, it's what David said. Reserve, extra. Right? If I have a reserve of bread in my pantry, right? It's the extra bread in my pantry. So breathing in extra volume. The amount of air you can breathe in past normal inhalation. And how much air can I breathe in past normal inhalation? Well, apparently 3 liters or 3,000 milliliters. And the way you would measure that is simply just have someone inhale and exhale, inhale, exhale, inhale, and before they try to exhale, say, no, keep going, keep going, keep going. Breathe in as much as you possibly can. And a little wheel spins inside of a device, and you measure how much air they can breathe in past normal amounts. Then they expire all that air back out again. Well, if inspiratory reserve is the amount of air you can breathe in additionally above tidal volume, then what's going to be expiratory reserve? The amount of air you can push out past normal expiration. And notice how little that is compared to inspiratory reserve. It's 1/3 of that value, actually. All right? And again, we can look at it as, all right, I breathe in, I breathe out, in, out, in, out, in, out, in, out. And before they try to breathe in, you say, no, just keep going. Before you try and just keep pushing all the air out of your lungs as much as you can. And you push all that extra air out. Now, nobody's saying anything, but if I push all the air out, or push out as much air as I possibly can, I should say, if I push out all the extra air that I can, have I pushed all the air out of my lungs, according to this graph? Haley? Have I pushed all the air out, according to this graph?
No.
Well, take a look. Does it reach 0?
No.
No, right, exactly. So you don't push all the air out, because if I did, that red line would go down to here, right? And that's a damn, ooh, I probably shouldn't, sorry, since you guys are posting me on YouTube now. You gotta find a way to delete all those things. It's a good thing that you can't push all the air out of your lungs. So imagine this, here's your analogy. Take an alveolus, and I want you to take a sheet of wet rice paper and fold the sheet of wet rice paper onto itself. And then pull it apart. Are you going to rip that rice paper to shreds? Yeah, you are, right? Because it's going to stick to each other. If I take my alveoluses and push all the air out, my 2 layers of simple squamose with a layer of water is like taking a wet microscope slide on a marble counter. Trying to pick up that slide ain't going to work. You're going to anneal the 2 surfaces together, then you're going to shred them as you try and exhale the next time. So it's a nice thing to actually leave a small volume of air to always keep our lungs minimally inflated. No matter how much air you push out, there's going to be a little bit of air still left inside of them. Otherwise, I would destroy them the next time I'm trying to inhale. Now, how much air could you maximally inhale and exhale in one big, gigantic motion? Well, that's going to be then your vital capacity, right? The max amount of air you can pull in and push out. So I take my normal inhalation, I breathe in as far as I possibly can, and then I exhale as far as I possibly can. And that distance right there is your vital capacity. another way I had to think about it, which was about, 11 years ago now, was the 50th birthday capacity. When I turned 50, my godkids had a birthday cake for me with all 50 candles lit. And it took a full breath of air to blow them all out. All right, I had some extra reserve, thank goodness, right? So I could probably do maybe 70 candles. We'll see in 9 years if I can do 70. But that's the vital capacity, right? The total amount of air you can breathe in and breathe out in one uninterrupted motion. Now, the volume of air that is left over between your vital capacity and no air at all is your residual capacity. This is 1,200 milliliters, 1.2 liters on average. This is for the average person. Right? Different people have different chest sizes. This would not work for Michael Phelps. You guys know who Michael Phelps is, right? Really big, gigantic chest. His numbers would be bigger, right? Someone, actually I just learned something interesting. So remember our endocrinology discussion of excess amounts of growth hormone during bone growth? I'm talking about Robert Wadlow. I was reading an article while the rest of you were in lab this evening, and when he was 8 years old, he was 6'2". When he was 8, okay? Big chest, right? When you get really small, you have a smaller lung capacity, so someone who's, quote, petite will have smaller volumes. But the proportions would always be the ratio, the same. All right, let's talk about the composition of air. I'm going to give you guys a little bit of a break. What is in air? Can you guys name all the gases found in air? Well, not I won't say all, but the major ones. So you got oxygen, nitrogen, CO2 or carbon dioxide, right? So if we had, you guys said oxygen, you guys said CO2, you guys said nitrogen. Which one's the most abundant? Do you know roughly how much? How much do you say, Dave?
78%.
Yeah, around the 79. Different books will have between 77 and an 80 number, right? So we're going to just call it 79 because that's the average of what most books will say. What is the percent of oxygen?
21%.
Does anybody know?
21.
How much?
21.
21%? Well, hell, I'm no math genius, but that looks like 100% already. So how much is CO2? You can already tell it's teeny tiny. It's 0.03%. That's not a whole, well, actually, I have to correct myself. It's now 0. Brain, think for God's sakes. 0.04 due to climate warming. They've actually increased it a little teeny bit from my first set of physiology books.
Well, now let's be careful about what's the cause.
I didn't say the cause was.
No.
And we're not going there. Right?
So
So
the
now,
warming
so,
is because of the CO2. The CO2 is not because of the warming. You always talk about that in the physiology, about why things happen as opposed to the effects.
I didn't say we're actually we're not even causing this. So let me ask you guys this: 21%. Is that sea level? Is that how we got that number at sea level? So what's the percent of oxygen at 30,000 feet? Is it gonna be less? Heck no. Come on, guys. Basic science.
Well, some of it's O3 at 30,000 feet.
No, Dave, stop. You have a big, you're a god. You just created a planet called Earth. And you have a big balloon full of air. And you pop that balloon. What happens to that? Where's that oxygen going to go? What's John's trivial pursuit, default answer? Oh, you guys are horrible. I'm going to make your lab practicum really tough now. Well, you then reply. What's the rule about diffusion? Where do things go? Until what happens? How long has there been air on our planet? Well, roughly about at least 3.2 billion years. It's reached equilibrium. Right? Regardless of being O3 or O4, you are going to have 21% O2, no matter where you are in the atmosphere. It's always 21%. It's always 21%. Now with that, then we go for a bit of a break. Solubility issues. which means how easy to dissolve in a liquid. CO2 is the most soluble. The second most, a little bit less soluble, is O2. And actually CO2 is about twice as soluble as O2 is. And then there's an intentional gap in the slide. That's there on purpose. Because nitrogen is really, really, really not soluble. It's way, way, way down the list in terms of comparing between CO2 and O2. But keep in mind, what is our most abundant gas? When you guys breathe in, it's nitrogen, but it's also the least soluble of these three gases that we have. Thankfully, O2 and CO2 are hydrophobic, they're lipid soluble. That means simple diffusion across cell membranes, no transporters, no carriers, no Ubers are necessary to get them across the cell membrane. So it's easy for them to do external respiration, internal respiration, and cellular respiration. All those places we can do exchange of gases. All right, give you guys about a 10-minute break, then we're gonna do some chemistry laws.